All right, everybody, density of liquids. You should have just done the video that was right over there that showed you the equipment setup. Pretty quick, and I can be pretty quick here as well. I should also comb my hair at some point, huh? So some important points you're going to need. More dense liquids sink, less dense liquids flow. So maybe you think of the salad dressing that you did in the previous example during your notes. Like before, a cubic centimeter and a milliliter are the same volume. They're interchangeable. 1 milliliter of pure water is a gram. By definition, that's what they said a gram is. 1 cubic centimeter of a very common substance, that being water. So you should be able to then figure out what the density of water would be. Well, if you had 10 milliliters, it would be 10 grams. If you had 100 milliliters, it would be 100 grams. So what's a number divided by itself? 10 over 10, 100 over 100, a million over a million? No matter what, it's 1. So the density of water really should be 1. When you do these, here's a quick check. If you make a mistake with mass, which isn't unusual, these are going to look funny. Your densities should really all be in the ballpark of 1. Some are going to be a little more dense than water. Some are going to be a little less dense than water. If they're like in the way away from 1, something's wrong. Let me know. We'll help figure it out. Density, mass over volume. We've done that plenty by now. And there's another little paragraph at the end. I'll show you that. So liquid, you can really just in here. I don't want to write it in here because this isn't the saved version. Write liquid 1. Liquid 2, liquid 3, or just 1, 2, 3, 4, 5, whatever. Number the 5 liquids. Give me the mass, give me the volume, and density is mass over volume. Round 2 decimal spots in this case. Little question about the layers. You should have seen that already in notes. This is a reference table of our atmosphere. You live down here in the troposphere. That black line would be the surface of the Earth. You live in the troposphere. Mountains, plains, everything's really in there. And then as you go up, 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 there's higher layers of the atmosphere. So think about it. Which one would be the most dense? It's the same concept as this layered, whatever that is, layered thing of liquids. Ooh, we did that one. There was a freebie. Rewind this video about a minute if you didn't catch it. Did our results confirm this? So you'll have to see which one you think is water. Maybe I'll tell you. I don't know. But either way, did your water one end up being close to that? What might have happened to be inaccuracies? Could anything have possibly gone wrong? Lots of things. Think about the steps that you did in this lab. Where might there be an inaccuracy? This is actually a Regents question with a Kelvin and Hobbes question. See what you think. What if we use bigger graduated cylinders? What would that do? I don't know. Let's think. Now I like this question. This is going to look like a little confusing and intimidating, but I want you to explain density, and I want you to explain what's going on here, and tell me basically the gentleman that wrote this is a very, very smart guy who does these little experiments to kind of help earth science teachers learn new demos, things like that. So he did this at his house, took some salt water, took some fresh water, and took a little plastic Easter egg with a very specific amount of like coins or fishing sinkers or something until it sits right about there, totally on its own. So what's going on here density-wise? Why does that happen? Explain it. And again, explain it as if you're explaining it to somebody who hasn't done all this density work. Give me a nice, thorough explanation here. Then you're done. Thank you very much. Good job. That's kind of the more intimidating, more difficult of the early labs. You've done it. More to come. Take care.